won't be an not a minimal. See, this is not a minimal problem. Because why it is not a minimal problem? See, G of 9 is required, the 3 is required only in certain polygons. If you take a 9 vertex convex shape, you require only one. So, this is not an optimal problem. So, that is why I say the optimal problem is actually an NP hard one. This is not a minimum. So, what we are actually trying to do is not to find minimization problem. So, this problem is actually called as a max over min problem. So, it is not an optimization problem in that sense. So, this is called as max over. Why it is max over min? So, you try to find out what is the minimum number of gods for a 9 vertex polygon. So, for some 9 vertex polygon it could be 1, for some 9 vertex it could be 2, for some 9 vertex it could be 3. So, you are picking the max over all the mins that you have taken out. So, it is not the min that you are taking, it is only the max over the min that you are taking. So, it is a very important paradigm as he pointed out. So, it will not be an direct optimization problem which you can pose. So, this problem is actually not an optimization problem, that which is many times it is construed that we are finding a minimal. We are actually, unfortunately, we are, though we kind of want to find the minimum, we cannot do that. So, it is always that we are trying to do is max over min is what that. So, most of the odd problem which are also called as set cover problems, you might have heard of set cover problems, they are always NP hard. So, in this case also, unfortunately, we are not trying for an optimal solution, because if you apply this solution for a 100 vertex convex polygon, it will give 33 as the number, but whereas we know that it will require only 1. So, this is not going to lead to an optimal solution, it is always a max over min on that. Okay, that is why with this problem is also a little intricate on that. Okay. Now, this is a conjecture after all our Rangoli experiments, we kind of conjectured that G of n has to be floor of n by 3. Okay. Now, the one thing is that, okay, maybe we will also go to the proof of this, which is also very interesting. It is not very heavy mathematics and all, it is also more Rangoli again. But one more pressing question, okay, which would be really fascinating to look at it. Okay, suppose you place guards at every vertices in any of these polygons, correct? Place guard at every vertices in any of the polygons. Will it cover the entire polygon? You have a 9 vertex polygon, I place guards at all the 9 vertices, will it cover the polygon? How can it not cover the polygon? What stupidity, you are asking some stupid question and making us think, right. So, the same thing, if you have a 100 vertex polygon, what would be his answer? So, if I place guards at every vertex in that 100 vertices polygon, then it has to cover the polygon, right. This is looking like a laughing stock. Now, you think about the same question in 3D. I place guards at every vertex in a polyhedron. Do you think it will cover the polyhedron or not? Whatever, it is not just, it is not non-simple or it does not have self-intersection, it could be non-convex. What is your answer? So, will it cover the entire polyhedron if you place well? Okay. So, he needs some time, he needs to show some actions, I think. It will cover. Any contradiction? Like if you have a cube, very simple example, and it has to cover, right. If you place at all the guards at all the vertices of a cube, it has to cover. Lowest number is maybe what? What is the lowest number of vertices in a polyhedron? Lowest number of guards. But the question is that whether placing guards at every vertex in a polyhedron, will it cover the polyhedron? Okay, is very sure. Yeah, same thing only. What are the assumption that we have as 360 field of view, except that it cannot pass through the walls or the edges of the polygon or a planes of the polyhedron. Okay. So, will it cover? No, not necessarily convex shape. Okay. Non-convex shape? Can you draw one or two 3D shape? One 3D shape can you draw? Cube, apart from cube and tetrahedron. So, draw something like this one in 3D, that is Z. So, what is your answer to that question? So, will it cover, will all the gods placed in all the vertices of polyhedron, will it cover the entire polyhedron? Yes? Is there anybody want to say no? Nobody wants to put their head on the anvil, I think. So, is there any polyhedron where you could think of placing gods at all the vertices and some dam is not covering the polyhedron? So, it is very difficult to think of, right? Almost impossible, isn't it?
I feel there is some possible.
Yeah. So, there are polyhedrons where if you place vertices on all, sorry, where you place gods on all the vertices in a polyhedron, it will not cover the entire polyhedron. Obviously, it is impossible to think of such a polyhedron, isn't it? So, we are all limited, that is what I said, we all know very little, to the extent that we do not know anything actually. So, it is very difficult to think in 3D, because even in 2D many times we will hard pressed to figure out. So, in 3D we just are hopeless, we cannot just do anything, we can't just imagine 3D and all, it is impossible. So, note down, one of the famous polyhedrons is called as the Carnot polyhedron. Obviously, the spelling is little tricky. So, look at the Carnot polyhedron. I do not know whichever word you want to make silent, I leave that to you. I think I am right, but I think I am right in spelling it correctly, but I leave that for you to figure out. But there are several polyhedrons, not just one. Okay, we will just do that classification. That actually leads to an entirely several different classification on that. Okay, this Carnot polyhedron with what I could spell, but there are several polyhedrons. That is not the only polyhedron. Okay, and you can also construct if you know something on modeling side. I did not bring that example. Okay, now we will just go into little bit of this conjecture and maybe try a proof for this conjecture, then it will be clear on the 3D side also what could be the reason, though it might still be difficult to figure out a polyhedron of that nature. 3D I do not think it is even valid, because there are some polyhedrons where it is not even possible. If you place vertex at a all, so that will classification we will see, because the moment you show one failure case, that is sufficient, right, because there is no way that you can cover with entire polyhedron. So, it is kind of little difficult in 3D, because 3D also people have you know, then how do you do something in practice, right? You have to have something in 3D. How long I can live with drawing some rangolis with 2D polygon and then say that I am doing something great, and when I bring some shape I cannot figure out what is happening on that, but it is there, you can do it in 3D also. We ourselves have done that, so that is why I am reasonably confident. Okay, so this thing will be little clear when you go into the proof of this. Okay, there is something called as, lot of proofs are there. One of the famous proof is called as the Fisk. Note down the name, Fisk's proof of sufficiency. So, remember also this max over min tells you that these gods are sometimes necessary, but always sufficient. Why? Like 3 gods are sometimes sufficient, sometimes necessary, but always sufficient. Why it is sometimes necessary? Because in some polygons of 9 vertices 3 is not required. Okay, it is always sufficient no matter what kind of polygon you turn out for n vertices and 9 vertices on that. So, this necessary and sufficient one is also a very tricky, many times it is confusing little, but we will stop with this max over min. So, how do you prove that? That is where this Fisk came, and very elegant proof that he brought in on that. Okay. So, how does one prove that? Of course, it also does a lot on graph theory and all. We will try to safely negotiate, minimize those kind of graph theory discussions, and you have done a course on graph theory? Huh? Okay. So, we will maybe apart from him, anybody else have done course on graph theory, or at least graphs in data structures and so on? I have used data structure course and no graph. Okay. that is okay, small is more than sufficient, maybe necessary, but it is definitely okay. So, we will leave that part and we will leave that, you can understand, it is not a big deal to understand in this particular case, at least we are not looking at the graph isomorphism, all that things and so on. We are not going to be a heavy graph theory. So, now we will have to continue with the more rangolis on that. Okay. So, I am going to define something what is called as a diagonal in a polygon. Okay. So, diagonal simply refers to connecting two vertices in a polygon. For example, if I connect these two vertices, it is called as a diagonal. Why? Well, it is called diagonal. That is by definition, but this guy, any two vertices that you connect, that guy, that edge has to lie within the shape. For example, if I connect where is our other color pens? Okay, suppose if I connect some other two vertices and this edge may lie completely outside. For example, if I connect these two guy, okay, this is not a diagonal as per our definition. Technically, we can distinguish an internal diagonal and external diagonal. Okay, so what we are interested in the internal diagonal, but these internal diagonals also have to be non-intersecting. So, what does that mean? Okay, so maybe in this shape. All seem to be coming. Okay, so when I draw two diagonals, it should not intersect. Okay, this it's not clear. Okay, so there may be some cases, let's say if I have a vertex somewhere here, okay, just as an hypothetical case, and if I try this, these two may be connecting these two vertices, and this entire diagonal, so to speak, is inside this shape. Okay, but then this is actually crossing another diagonal, which you should not do. Got the idea? So, if you draw any polygon and then you actually draw all the possible non-intersecting internal diagonals, then you tell me what is your observation. So, take any polygon, preferably take a non-convex polygon, and then add diagonals which are all internal, and then they are non-intersecting diagonals. So, try all possible diagonals, of course, they would be intersecting only at a vertex, which is fine, but non-crossing, they should not cross each other on that. Okay. So, yes, maybe a simple case like if you take a square or rectangle, so you cannot have both these diagonals, both are valid internal diagonals in, individually. So, you can either have one or the other diagonal, not both, and then you should cover the entire, or you should put as many as internal diagonals and leave no possibility of missing. N minus 3 or n minus 2, n minus 3. Okay. Okay, other observation, anything else? Anything, any key observation you can come out with that. So, once you add all the internal diagonals, what is that you can think of about that particular polygon after adding all the internal diagonals? So what happens? So, it has split the entire polygon into others. What is your observation? So, are all observing that it has split the polygon into n minus 2 triangles. I mean, triangles is sufficient for me, n minus 2 we can. So, do you observe that it has split the polygon into set of triangles. So, this is what is called as a partitioning problem generally in geometry, but in this particular case we are partitioning a polygon into set of triangles. Okay. There are other partitioning like a convex partitioning, many other monotonization, so many are there, we will probably leave out all that, but in general this is called as a partitioning problem, which is also a popular problem in geometry. But in this particular case we are specifying a specific case of triangulation as being a the key thing on that. So, what will happen in this particular case if I keep doing as what he observed. So, it will actually have n minus 2 what n minus 2 triangles and n minus how many diagonals you will have n minus 3 diagonals. Well, that will differ the proof of that, but so you just can imagine that I will have add one more became terrible. So, you can see that the entire polygon has been divided into set of triangles. Okay. So, of course, this triangulation is also what is called as a graph, if you are aware of graph terminology, but I think we will have to bring something on the graph, but we can also avoid that maybe. Okay, then we will directly go to. Okay. So, all of you have some shape where you have triangulation done, is everybody? Some people are not nodding head in any direction, some people had nodding in all directions. So, I do not know what that to make out of that. Okay. So, assuming that you have done some triangulation, okay, so what we are going to do is to do what is called as a forced coloring. Okay. There is something in graph called as K coloring, but we will do what is called as a forced coloring, okay, which without going into too much of details. So, you take 3 colors, okay, or what is that you will take after that? Red, green and blue, RGB or RBG either way, okay, and do a forced coloring for each of the triangulation. What does that mean by that? So, suppose if you start with R here for this vertex, okay, and remember this is a triangle here. So, if I put G here, okay, this has to be B, okay. So, R, G and B, and then since this edge is also having R and B, so for this triangle this has to be G, okay. Now, this is B and G, what about this one? This is R, and since this is R and G, this has to be B. So, you do that on your notebook and tell me what are your key observations. So, this is come from a principle called as a graph coloring or a K coloring principle, where in this case K is 3, but we can understand without all that also. So, what are your key observations? This is a diabolical one actually, this is not exactly the correct one, but anyway let us look at what your observations are. But before that there could be one more observation on it, you are right. Correct, but slightly can you refine that? So, you talked about minimal, but can you refine it little better on that? You are right that minimal is also a valid point. Maybe you just refine that, you think about it. That is not exactly what I was looking at, but you can still refine it and then you are kind of there, but of course, the minimal point is correct one, but before that I want to touch upon one more aspect of that. So, what are your observations? So, you have placed, remember this is called as a forced coloring, you do not start from somewhere and then again restart from coloring the scheme from some other vertex of a polygon, you do not do that, you go in a very orderly manner on that, this is called as a forced coloring on that. So, what are your observations from that? As he pointed out, one of them could be if you just place guards at those minimal number of colors, then you will cover the polygon, that is also kind of, but any other observation that you can do? That is actually not necessarily true, that is why I said whatever I have drawn there is not exactly reflecting the general idea, you will not have that in your thing, check that, you will not have that. If you fix the guards at which edge? Correct. Correct, that is a forced coloring idea itself. So, any more deeper observation on that? leave it. I think what he said is that every color will get forced once you fix R and B on one edge. Everything will get fixed after that. It's correct. That's how we anyway do the force scheme on.
All the colors are approximately equal number of times.
No, not required actually. Not necessarily true on that.
One above one below.
No, that is also not necessary. Ah. Number of guards that you require. Okay, everybody has jumped one step ahead, but he also did the same thing and placed the guards at the minimal number of colors that it turns out will also cover the correct. But anything before that? Yeah. Any other observation? Okay, so I think all of so any other observation what I am trying to hint at is that you could place guards at any of these colors. You could have pick R as your choice or B as your choice or G R as your choice. It will actually still cover the entire polygon. Well, that need not lead to a minimal in number actually. We are actually not looking at right minimal as such, but this will still cover. So, in this particular case this is a very skewed one. So, you can just place guards at these two R's, right, this one and this one, this will also cover the polygon, or replace here and G it also cover, and similarly in this case is a diabolically every guy became 2, which is not necessarily true in general case of that. So, out of that you can pick the minimum also. So, what is the reason that even if you pick the minimum of all the colors it is still covering the entire polygon. So, why is that? What is your first statement? But how does it cover the entire polygon? They like use the hint is that use the idea of triangulation itself to reason out that. Yeah, it is something like that. So, you can imagine that like each color is actually part of some vertex in a triangle, okay. And if you look at that, they will actually cover the entire set of triangles, each one will cover some set of triangles, and putting together it will cover the entire set of triangles. That is because every vertex is part of a some triangle that you can think of. So, if you take a G, okay, G has certain set of triangles, and you can see that G both put together will actually cover, because you can see that that is part of your triangulation already that is coming up. So, if you take an R, R is part of several triangles, okay, and then because every vertex is actually covered in some triangle, and you do cover all the vertices by means of the coloring, and it has to cover the entire polygon. So, you can pick any of these out of these 3 colors on that, we will still cover the polygon. So, naturally what is our inclination would be, we will pick the minimum of the colors that we have obtained from R, G and B on that, okay. But that does not still tell what? That does not still tell it is n by 3, right. We have done all the work, but where is n by 3 coming in here? So, we have found some coloring scheme and nicely working and find the minimal, okay, we will get some number, but how do you know that is still n by 3 on that? RGB is 3 colors, but that is 3. Now, where do you put that 3? Put that top, or where is n coming in? It will be n into 3 or n by 3 or 3n or 3 by n. You have a 3 there, but how do you fix other guys after that? Because of triangulation also it is 3 only. So, how do you show this is n by 3, which is a very catchy argument, but also difficult to do that. Okay, so, one of the polygons that people have see all of for all rangolis in this entire thing, it is all about rangolis only. Whatever problem that you take, it is all about rangoli, and the conjecture will come from that. So, the worst case polygon shape apparently is what is called as a comb shape. You have seen comb, right? Everybody uses a comb, okay. So, this is called as a comb shaped polygon, that is being used in several other problems as well to show their argument. Okay. So, in this case you can, if you just look at a comb shaped polygon, so how many vertices this polygon has? Okay, this polygon has 12 vertices. Okay. Now you can see that there is a comb, and interspread with the comb that there is a edge here. Okay. How many edges you will have here on this, and how many comb that you have here on that? How many comb you have here? There are 4 combs. So, in this particular case, if you place the guards, it has to cover each of the comb, correct. So, what is the total number of vertices? Total number of vertices is 12. Okay. Now, you can see that each comb, okay, suppose that this number is that, you will see that it will be 3k, n equals 3k, okay, where k is the number of combs, because of the way I structured 1, 2, 3, okay, sorry 1, 2 and 3, then you can see again 1, 2 and 3, 1, 2 and 3, it keeps rotating, and after all the 1, 2 and 3, you will see that total number of vertices n will become 3k, where k is the number of combs here. So, each comb will need to be covered, okay, that means what is the number of guards? That means it is n by 3. Okay. So, this is also the one way, it is not exactly a proof, but this is kind of an observation on that. Okay. So, you can actually think of any number of vertices and come up with a comb shape, and if you have this comb, we can see this relation satisfying n equals to, do not directly put another connection from here, there will be an edge between 2 comb, then only this relation will get satisfied on that. Okay. So, it is also n equal 3k, it is based by way of structuring the polygon on that. Okay. But then what is the relation between this and coloring that we did, and how do you show that is an n by 3? So, the only one thing that we all could figure out, we have chosen 3 colors. So, the number 3 somehow comes from these 3 number of colors that we have chosen. Okay, that is only thing. Okay, now there is how do you prove that this is n by 3? We have 3 colors. Okay, so the beautiful argument, I do not know whether you are, I will try to put as best as I can. So, there is something called as a pigeonhole principle. Have you heard of that? If you have done something in maybe in graph theory, I do not know whether they teach this. They teach this. Yeah. Suppose that so you have n objects and k holes. Okay. Like you can think of n birds and k holes, something like that, k number of holes. Okay. So, you can easily see that at least there should be one hole which cannot have more than n by 3 objects there, little confusing. So, imagine if every hole you put n by 3 object, more than n by 3, that means what will be the total number? It will go n by k, it will go more than n. See, imagine you have 3 holes, and let us say there are 12 birds that you pack in on that. Okay. So, if you pack everything as 5 birds, what will be the total number of birds? It will not be 12, it will be more than 15. So, there should be at least one hole where you can pack no more than n by 3. There will be at least one hole where you cannot pack no more than 4 birds on that. So, if you pack every hole as 5 birds, then you will have 15 after that. So, there should be at least one hole where you can. So, you have n vertices and you have 3 colors. So, there should be at least somewhere you will have this n by 3 being used as the color to figure out the number of guards that you require. Is that argument okay or too much? So, this is a classical argument with a pigeonhole principle on that. Okay. So, the entire, after all the proofs, the entire final touch on the proof comes from a different principle which is called as a pigeonhole principle, with just both coloring as well as the number of vertices. Is that idea clear? So, this is the simplest problem that we have solved in art gallery. So, you can imagine so many other issues. What are the assumptions that we have made? Can you note down the assumptions? So, what are the assumptions that we have made? to prove something like n by 3 simple polygon. Okay. Then is that all? 360-degree. Then you cannot see through walls. Okay, that will become really a complex problem after that. Another one, like if you imagine a security guard usually, right, say any other. So what is that relation to what we have assumed, that is completely contradictory? Security, okay, it's always awake, but that's true. So he may not stay at his position, that's I am just flipping the statement. So he will always be moving, okay, that is called as a moving guard problem. How much he is going to move or she is going to move, we do not know, that will become another constraint. Or instead of 360-degree you make it as 180-degree, then the problem becomes mightily complex. I do not think less than 180-degree the problem is even solvable, not even possible. Okay. And then there is a moving guard problem, there is a prison guard problem, it is called as a prison guard problem. The policeman is allowed to move certain distance, but thief can move anywhere, that is what usually the case. That is called I think there is a hunter's problem. So I would say as an exercise, go and figure out what are all the various art gallery problems that has been studied. Is only the assumption. Okay. Suppose if we have a polygon with a hole, you may know what is a polygon with a hole. Like you take a paper and then you punch a hole, rectangle hole in the paper. So the polygon area is what now? Okay. So if you take a paper like from your notebook and then you punch a rectangle hole on that. Yeah, the area of interest is this region, correct. Now will same n by 3 holes. So can you do some experiment on that? Can you triangulate this polygon and tell me, then do the coloring and tell me what happens, whether it is also going to be n by 3. These are polygon with holes. As far as I know, this is the term. We can't say this as a complex polygon. Okay. Usually term this, see there are other terms is that, okay, if you are a topology guy, this is called this a simply connected and multiply connected. Yeah, so that's maybe math guys might have heard of this term simply connected. Have you heard of this term simply connected? Okay, so it comes from topology aspects. So we call, if you want a technical guy, these are classified as a multiply connected polygons. So that comes from topological path definition. So we will safely ignore that at this point, but really if you want to do a technical thing, yes, it is multiply connected polygons. Is it working? Yeah, missed. Okay, now do the coloring, RGB, the forced coloring you do. Hopefully we will get some coffee, tea soon, I think. So if you do you should do the diagonalization, okay, of this. So you can connect vertex like this, but not inside. Okay. So are you all clear of this polygon with hole and idea? Because don't connect anything on the interior, then that actually becomes exterior. Like for example, if you put a diagonal like this, okay, then this is not an internal diagonal, okay, this is an external diagonal for this case. So don't use that diagonal. Forced coloring does not, it's doubling back, right? Yeah. So it is R and R coming back. So you can, at least there may be some cases where it might work, but in most general case actually you will see that there is another guy going to come back and then knock off the existing color there on the. So this doubling back is happening on the, so that is come from a graph theoretical perspective, because the other one will eventually become a tree and this actually becomes a graph. I do not know if you know the difference between a graph and a tree. So the tree will have no cycles, or graph is a tree with cycle, or we should say the other way, a tree is a graph with no cycles. So that is what, if you are using from graph theory or a data structures, this polygon with holes will lead to something called cycles, and that is why the doubling back happens. So you can't use the same proof. or you could, but how do you now, how do you prove what is that number like n by 3, what is that number now? This is the simplest case only we are dealing with, right. So, what would be that number like n by 3 that we have? Any conjecture on that? Okay, I will give you a simple trick on this, okay, then you try this. So, now we all saw that this coloring led to a doubling back, right, it is not working because even though we did a force coloring, it is coming back and trying to knock off the existing color, okay. So, what you can do is that this is what I said, you make this polygon, okay. So, I will just draw another one. Okay, so deliberately I have left some gaps on these two, outside and inside. So, what you do is that you connect the ones that basically try vertices close by. So, then I just connect these two guys. So, now what can you say about this polygon with respect to what polygon with hole? Does this polygon has hole or not? No. So, basically we punch a line and add more vertices. Basically, if you punch one of the diagonals into 2, basically you split that edge into 2 and we become a, now the entire polygon with hole is actually becomes a simple polygon in our original term, or a polygon with simple polygon without hole we can think of. Now, you do the coloring here, naturally what will happen if you do that one? You should not double back, right, because this is anyway a, this is already a seen, okay. So, now can you, how many vertices we are adding extra? This is only one hole. How many vertices we are adding extra for one hole? 2. So, if you have a multiple number of holes, how many vertices you will be adding? 2 into h, let us say h is the number of holes. So, now based on this, what could be your conjecture for that n by 3, how does n by 3 will change? So, just tell what could be the number here. Divided by 3, correct, is n plus 2h or n minus 2h? But finally, you have to remove that, right, because those two are added extra vertices. That is total number of vertices that you have, okay. So, if you add, so just can you just tell that whether it has to be a plus or a minus? Plus, you are sure on that. So, the total number of vertices is going to be n plus 2h you are telling, because at every time we are adding 2 to make that hole into a non-hole category. So, that means for that number of holes is the 2h, the total number of vertices is becoming n plus 2h, and then you are saying n plus 2h over 3 on. That seems to be a reasonable expression, yeah.
How many vertices does
So, that is how you extend from a simple polygon case to a, or which is also a simple polygon to a polygon with hole, okay. So, now yeah.
polygon with hole has how many vertices? I can't understand.
Yeah, so the thing is that n is total number, like that is big, in this case what is n? Okay, in this case what is n? It is putting together both number of vertices. So, that is 8, you will not say that this is n1 and that is n2. We all look at both as n, if you want to split it, that also you can do, but we typically do not. So, in this case, that is why this also is become n and then plus 2 into h. In this case, it will be simply 2 only, because only one hole is there. So, this is total number of vertices. There is no non-closed polygon. There is no gap, we never consider a gap with a polygon with a gap. Yeah, so what we are doing is a polygon with hole into a simple polygon. That's what, so that means this becomes total number of vertices anyway. So, that will be n plus 2h. No, not required. No, no. I mean, I put a simple case. I mean, you can have a hole like this also. It still stands. Total number is still stand on that, right? But that is only one punch you are doing anyway. You are not doing multiple punches on the same polygon to have more. See, the moment you have one punch here, that will make your polygon with a hole into a polygon without hole, that is all. One punch is sufficient, where you can do wherever you want. I just did it in a convenient place for me to draw that. Yeah, you can just do that. So, you that diagonal you just split into two, that is all. Yeah, that one diagonal is split into two, the first one that you drew, right. You can split it in any one that you want, but I just had a convenient example, that is all. As long as you make that polygon with hole into a polygon without hole, that is what you are splitting on that. I mean, this is an idea of how to extend the proof from a simple case to a much difficult case. Of course, there are a lot of cases which as this problem can be like what we saw in 3D, right. It is the same statements are not going to. So, 3D we do not know. Okay. So, then for example, so how do you argue for like these polygons are nice with straight edges, we can have curved polygons. So, make all these edges into a curved one instead of a straight one, then we will still n by 3 hold. So, make all these into a curved edges, like for example, I could have a curved edge like this. It is not anymore a straight polygon. I mean, we may not have never heard of a polygon as a straight polygon. So, we can define what is a straight polygon, that means all the edges are straight edges. We can have a curved polygon, that means all the edges are curved. Well, that is where everything could become complex. Why? Because I can have a shape curve like this, I can have a curve like this, I can have a curve like this. Well, I can also have a curve like this. That we can simply define. Suppose you have all seen mosquito coil, right. How many guards are required in a mosquito coil? Huh? Oh, you are not seen micro. Okay, you can take a spring and then compress that spring not on a straight one. I have to define the process. Okay, if we draw that shape, okay, we will draw a simple coil. Okay, so something like this. Basically it does not even have a vertex. So, there is not even a notion of n coming in there. So, how do you bring the notion of n here? So, it becomes a very difficult problem now. The same ideas that we discussed so many last 1.5 hours, suddenly everything is vanishing now, right. But we have to handle this, right. People are buildings are coming up in this shape. Then how do you say, I do not know, no, I cannot place cameras because my teacher told me only polygon with straight edges and that is what I can handle. I cannot do anything more than that. So that is what it becomes a trial and error problem. What exactly you do is basically it's a trial and error problem. That is why it is an NP hard problem. It's basically done by a trial and error approach, not a correct way. It's called, I mean, it's typically called as a greedy approach. That is how we could solve this problem. So, there is no answering of an n by 3 here. There is no answer. So, it becomes a tricky problem to have. Now, you can imagine a same shape or a similar shape in 3D. Okay. So, now let us just before having tea. Okay. Now, let us just discuss one quick point, like why do you think there are some polyhedra, where if you place vertices it could not, it may not cover the entire one. But what could be the thinking, or what could happen there to have that statement not becoming true? Polyhedron, you mean? That is what you go to types cannot polyhedron. That is a complex one, there is a simpler one. I do not have that picture there on that. So, what could be the thinking of, see, we did all this triangulation, we did internal diagonals. So, in these polygons we always can say that we will have definitely at least one internal diagonal, right, at least one internal diagonal we will have. So, what could happen there in 3D? That means what? If you do the same thing as a tetrahedralization, which is a counterpart for triangulation, what could happen there? So, there are certain polygons where you cannot add any diagonals that are not internal. So, all diagonals that you add are external. Difficult to visualize all that. Saw that polyhedron, but this is the idea. So, in 3D what we have is what is called as a tetrahedralizable polyhedra and non-tetrahedralizable polyhedra, but I do not know whether any algorithm exists. Suppose I give you polyhedron, whether can you quickly tell me whether it is a tetrahedralizable or a non-tetrahedralizable polyhedron?